This is lecture 22, part 1. So in last two lectures, we have discussed what is Bode plot and how to get that asymptotic Bode plot. So today we'll discuss if there is any second order term, then how to draw that asymptotic Bode plot, and we'll solve one more example. So there is a small correction in last lecture. What I have discussed that this particular frequency, so here that frequency here, this is 0.2, and actually I said that here that would be the frequency is 11 and 13. It is not, because one decade after these two, that would be 20, and the other frequency one decade above, that would be 30. I said it is 11 and 13, so please ignore that. So this is 20 and 30. So that means the corner frequency, it is 1. So one decade below, that is 0.1, and one decade above, that is 10 here. And the second one is that corner frequency is 2. So one decade below, that is 0.2, one decade above, that is 20. And for 3, one decade below, that is 0.3, one decade above, that is 30. I said here this is 11, and by mistake it is said 11 and 30. That is not, that is 20 and 30. So today we'll first see, that means if we have a second order term, then what would be that asymptotic Bode plot. That is, if you have that term, that means like gs, g of s, that is a square twice zeta omega n s plus omega n square. We have seen represent it in normalized and scaling form that we have discussed. That is normalized and scaling form. So here we can write it in this particular form. So that is, if you write it here in normalized form, that is g of s by omega n square, and that would be s square plus omega n square plus twice zeta s by omega n, and here you have 1. So now if we just represent that s by omega n as s1, so that would be, say, gj omega by omega n square. Here it would be j omega whole square, because it would, here you would have s1 square, here you have s1 square, and here you have s1. So in place of s1, I am just replacing j omega square. You can see that s1 is, we have done it here, twice zeta, that j omega plus 1. So now if we just draw that asymptotic Bode plot, how it looks like in normalized scale. So this is that logarithmic scale frequency, and that is in dB, and here that is 20 log of that Gj omega divided by omega n square. So this, that is actually in normalized form. So if we plot that one, so suppose omega n, that is omega n is that corner frequency, we have seen that one. So then that asymptotes would be below that corner frequency, it is approximately equal to 0, and this particular slope, it is 40 dB per, it is 40 dB per decade. We have seen that one. That means if we have a factor like s plus a, it is 20 dB per decade, but if you have second order term, we have seen that it is 40 dB per decade, and at natural frequency, at omega equal to omega n, at corner frequency, that angle would be 90 degree. So here we have seen that that slope is 40 dB per decade. So this is that asymptotic Bode plot. Now one interesting thing that we have discussed in last class, that means if we calculate that what would be the actual magnitude. So actual magnitude is this one, that is omega n square minus omega square, this thing, and at omega equal to omega n, that means at corner frequency, you can see that this term would be equal to 0, but that this term would be there. That depends on that zeta value. And here, if we vary that zeta, that means if zeta is very small, okay, so that important thing is here, that is actually omega by omega n. That means it is that scaling, that in x-axis it is represented by omega n, and that is in log scale. That is in log scale. So again, that whenever we are drawing that asymptotic Bode plot in normalized and scaling form, so in x-axis we have represented that 20 log Gj omega by omega n square, and in x-axis that would be omega by omega n, that is in log scale. And here that natural frequency, it would come, that corner frequency, it would be 1. We have already discussed, because if omega by omega n equal to 1, if omega by omega n equal to 1, so then omega equal to omega n is the corner frequency. That means if we represent it in only omega scale, log omega scale, so then the corner frequency would be omega n here. But if we represent it in scaling form, that is by omega n, then this one would be 1. And here, what would be the correction at this particular point? That means at corner frequency, we can see it here, that whenever zeta is small, that means it would be, suppose this is 0.1, so suppose this is 0.1, when zeta is 0.1, the correction would be like this. whenever we increase that zeta value, say suppose the zeta is say 0.2, so then that would be 0.2 zeta, and if we keep on increasing that value, then we will see that the value is, the plot is coming like this, and here this is that zeta which is greater than 1. So what we have seen here, that means whenever we have a second order term, the second order term, then we can represent it in normalized form that we have discussed in last class, and in x-axis that it is represented in the form of omega by omega n, that is in scaling form, and in y-axis it is 20 log of gg omega by omega n square. So if we do like that, then the corner frequency would be equal to 1. Corner frequency is 1. Corner frequency is 1, and if we go for normal omega scale, log omega scale, so then that corner frequency would be omega m. That thing we can see from this particular relationship. Now what would be that asymptotic Bode plot? Whenever that zeta, so zeta greater than 1, that Bode plot, asymptotic Bode plot would be like this, and when zeta say less than 1, whenever it is very small, then that asymptotic Bode plot is like that, and for different values of zeta it would be looking like this. So now let us see what would be that phase. So the phase, as we have seen, whenever it is a second order term, then we have seen that, so it is also in the scaling form. When omega is very high, so then that angle would be 180 degree, and that slope would be 90 degree per decade. And here that corner frequency is 1 because it is in the scaling form, and here that is in degree, that is in degree. So now, so 1 decade below this, so we take that this is say 0.1, and 1 decade above, say this is 10. Then what would be that slope? Slope is, that means at corner frequency, this value is 90 degree, and when it is very high, 80 degree. So like that first order term, you take 1 decade above that corner frequency, that is 10, and 1 decade below, that is 0.1. So then that would be, so that would be that phase plot, and here this is 90 degree per decade, the slope is 90 degree per decade, and this one is 180 degree, because whenever it is omega is very high, that angle goes to 180 degree, that we have seen. Now what happens whenever zeta varies? Because we have seen that at omega equal to omega n, that means at normal, at corner frequency, that angle remains always constant, that is 90 degree. It is independent of zeta. But whenever you move from that corner frequency, then you can see that that angle function of zeta, that angle function of zeta, and when zeta varies, that means zeta is very small. So like that gain plot, so it looks like that. So whenever here that zeta is very small, say 0.1, and if you increase that value of zeta, so then it looks like that. So this is say zeta 0.3, like this. That means there is a correction when, and the black one is zeta equal to 1. This is zeta equal to 1. So that means whenever we have second order term, so we can represent it in normalized and scaling form. If we do not represent it in normalized or scaling form, then what happens? The corner frequency would be omega n, and below that omega n it would be taking some value that we have discussed, that whenever it is not in normalized form, then we can see that at low frequency the value is this one, 20 log omega n square, and at high frequency it would be that 20 log omega square with the slope is 40 dB per decade. But if you take it in normalized form, then we can see that low asymptotes is 0 and the corner frequency is 1. So we have considered here that normalized form, so the corner frequency is 1, and below that corner frequency it is approximately equal to 0, and its slope is 40 dB per decade. And here this is that phase, that slope is 90 degree per decade. In case of only S or S plus A, we have seen that slope is 45 degree per decade, and here it is 90 degree per decade, and we can see that phase and gain both depend on zeta value. But in case of phase, when we are at corner frequency, that angle is always 90 degree because it is independent of zeta, and for different values of zeta we can see there would be some correction. So correction means whenever we draw that asymptote, if zeta is very small, so then these corrections we can do it at the corner frequency. So now let us solve one problem, and I'll be just showing here that magnitude plot. So I would suggest you all to plot that phase on your own, because we have done that phase plot in case of say only first order term. So here let us see just an example. So suppose that loop transfer function given as gs equal to s plus 3, s plus 2, and we have one second order term, that is s square plus 2s plus 25. So the first step would be taking that common here, 2 into 25. So then we have s by 3 plus 1, and below we have s by 2 1, and here we have s square by 25 by 2 by 25 s plus 1. So here we have two first order term and one second order term. So let us, and there is a constant that is 3 by 50. So let us draw the magnitude plot. So here that is log omega, and this is in dB. So now let us see what would be the magnitude plot of this particular transfer function. So first we take 3 by 50. So then there would be a constant term, that is, suppose this is that constant term here, and that would be 20 log 3 by 50. So this is that value, and the corner that frequency, that is 1, and this is 10, this is 100. So mind that we are now plotting in omega scale, that is not in normalized form, not in scaling form, and here it is in dB, not in normalized form. So now what would be the asymptotic Bode plot for S by 3 plus 1? So there would be some corner frequency, and that corner frequency is here, say suppose 2, and here you have say 3, 4, 5, like that. So they are not in scale, just I have shown that those are the frequency points because 1 to 10. So now for the first term, that is by 3 plus 1, the plot is corner frequency is 3. So corner frequency is 3. So the asymptotic Bode plot is up to 3, and then that is in numerator. So that plot would be like this, and here that slope is 20 dB per decade. So this is that plot for S by 3 plus 1. So now let us see what would be the plot for this particular term, S by 2 plus 1. So here that corner frequency is 2. So the asymptote should be like this, and as it is in the denominator, so the slope is like that. So here it would be for S by 2 plus 1, and this slope is 20 dB minus 20 dB per decade. So now let us see what would be the plot for this S square by 25, 2 by 25 S plus 1. So here that omega n, we can see that omega n is 5 because that is omega n square, and as we have discussed that corner frequency would be omega n. So the corner frequency is 5 here, and we can see that plot, that means for this particular one, because we have taken that 25, that omega n square term here, and already we have plotted that 20 log 3 by 50. So for the second order term, that is in the denominator, then we can see that it goes like this. So up to 5, and then the slope would be different because that slope is 40 dB per decade. So here that is in the denominator, so the slope is So that is actually 40 minus 40 dB per decade. So now we have drawn all the asymptotes for individual terms, and then we can see that what would be the resultant. So the resultant is it starts from here, it goes like that and up to 2. Now from 2 to 3, here there is only one slope, and that slope is here, that slope is minus 20 dB per decade. That slope is minus 20 dB per decade. And then we can see that from 3 to 5, there is one negative slope and there is one positive slope. So then that would be flat up to 5. So this slope is 0 dB per decade, because this is that negative slope and this is positive slope. And after 5, so this slope and that slope will be cancelled out, so only extra slope is there, that is 40 dB, minus 40 dB per decade. So that means here we can see that there would be a slope that is minus 40 dB per decade. So minus 40 dB per decade. So now one thing we can see, that what is that zeta. So that means twice, that is 2 zeta omega n. Here that is a square plus twice zeta omega n plus omega n square. So twice zeta omega n equal to 2, and what would be that zeta? So zeta equal to 1 by omega n, and you can see that the omega n equal to 5, so that means it is coming 0.2. So whenever there is zeta equal to 0.2, so there would be a small correction around this particular point 2. So that means here we can see that the asymptote should be like this. The reason is that zeta is coming equal to 0.2. So because of that one, so there would be a small correction here. That means this one would be say like that. So that means whenever we draw that asymptotic Bode plot, so that asymptotic Bode plot, say suppose one transfer function is given, and we can just take it in this particular form. And what we have done in this particular case, there is one second order term, and for that second order term we can see that slope is minus 40 dB per decade. And then because of that zeta values, zeta is not equal to 1, that is zeta equal to 0.2. So then there would be a small correction. That correction is shown here around that corner frequency. That corner frequency is 5. So what we have done in the Bode plot, that means we have discussed the different factors, and first order factor is 1 by s plus a, and second order term, and here we have taken that second order term and we have shown, that means what would be that asymptotic plot. And here it was in the numerator, that means the denominator is 1. So if you have only that factor, your asymptotes looks like that. And whenever it goes to the denominator, we have shown that its slope is that negative, and we can show all the components and its corresponding that asymptotic Bode plot, and this is that black one is that resultant one. So that phase plot, I would suggest all of you to do it on your own, because only one thing is, for this particular second order term, you can see its corner frequency would be 5, and if you take one decade below, that is 0.5, and one decade above, that is 50, so 0.5 to 50 with the negative slope, it has minus 90 dB per decade, and the other factors already we have discussed, so those things can be done easily. And at the corner frequency, as zeta equal to 0.2, so you need to correct that one as we have done like this. So this is all about that asymptotic Bode plot. So let us discuss two important concepts in control systems analysis and design. So one thing is, there is a class of system which is called that non-minimum phase system. So there is a class of system which is called that non-minimum phase system. So this is a class of systems. Its name is non-minimum phase system. So now I'll be just giving you some idea why it is called non-minimum phase system. So by definition, this is a transfer functions, those having poles and or zeros in the right half of that S-plane. So that means if you have a transfer function, and if the transfer function have pole and or zeros, that means if there is a zero on the right half of that S-plane, so then it is called the non-minimum phase system. And conventionally we take, so by definition, if there is any pole or zeros on the right half of that S-plane, but conventionally in control systems we normally say that if there is one zero on the right half of that S-plane, then it is non-minimum phase system. So let us just write the definition, that is the transfer functions, those having so this is very important because it has lot of practical implications. You can see poles and zeros. So that means if you have a transfer function, if it has pole or zero on the right half of that S-plane, so in the right half of the S-plane are known as non-minimum. So this is very important, non-minimum phase system. So we have discussed it in the time domain analysis. That means if there is a zero on the right half of that S-plane, we have seen that what would be the time response. So that means if this is t and this is say yt, if there is a zero on the right half of that S-plane, we have seen that there would be one negative kick and it goes like that. So that negative overshoot would come, and we have seen that one. So that means if there is a pole or zero, there is a pole or zero in the right half of that S-plane, then this is called that non-minimum phase system. But conventionally what we take, if there is only a zero on the right half of that S-plane, then it is called that non-minimum phase system. But by definition, if there is a pole or zeros. So let us see. So practically there are many examples like So this bicycle is also one example of non-minimum phase system, and there are some converters. So you can see that there is some zero on the right half of that S plane. So there are many examples, and also you can see that inverted pendulum, if you just derive the transfer function, that means in the linear, it is a non-linear plant. So if you linearize it, and you will see that 0 would come on the right half of that S plane. So there are many examples where which are actually non-minimum phase system. Why they are important? Because if there is any 0 on the right half of that S plane in the root locus, what you have seen that if there is a 0, whenever you start increasing that value of k, that one pole will be moving to that 0. So after a particular value of k, that system would be unstable. So that means it actually restricts lot of constraints in the design. So those things will be discussed in second part of this course. That means if there is non-minimum phase 0, what type of problem you would face in designing a controller. So now we'll just see why it is called non-minimum phase system. And the most important thing is that magnitude and phase, are not uniquely related. So this thing we'll be discussing now. What is the meaning of that? So suppose we take a transfer function that is g1 of s equal to s plus 2 divided by s plus 3. So then we can see that its magnitude is coming that omega square plus 4. That means if you just replace that s equal to j omega, then you would get that this is that magnitude. And what would be the angle? So that tan inverse that omega by 2 minus tan that omega by 3. So this is that angle. But if you take a transfer function that is g of s, which is s minus 2 by s plus 3. So according to your definition, that means if there is a pole or 0 on the right half of that S plane, so here you can see that there is a 0 on the right half of that S plane. So that's why this transfer function is called non-minimum phase system. But why the name is given non-minimum phase, that we are trying to understand. So this is, we can write it like S plus 2 divided by s plus 3 into s minus 2 by s plus 2. So this particular transfer function can be written like this, and you can see that this particular term is nothing but this term, but we have one extra term, that is s minus 2 by s plus 2, and it is clear that this particular factor is called that all pass factor. So all pass factor means all pass transfer function, that means its magnitude is 1 all through that frequency. Now let us see what would be the angle. So that angle is, you can see here, so for this particular transfer function, we have that gain and this particular phase, but this particular term is introducing some extra phase. What is that? That is here tan inverse omega by 2 minus tan inverse omega by 3. So contributing extra phase. So what we have seen here, whenever there is a 0 on the right half of that S-plane, we have seen that that can be represented as the product of two factors, and the first factor is similar to that G1 of S. That means two poles and zeros they are in the left half of that S-plane, but there is one all-pass transfer function, and this all-pass transfer function, its magnitude is always 1. So we can write it here that magnitude is 1 all through the frequency. So it is not changing any magnitude, but it is contributing this particular phase. So this phase is that extra phase, and this extra phase is coming because of that right half of that 0. So you can see this one, and if you just compare with this G1 of S and G2 of S, what we have seen, G1 of S and G2 of S have the same magnitude, because this all-pass factor is not changing that magnitude, but you can see its phase is more than. So that's why the G1 transfer function, it is a minimum phase system, but G2S is not a minimum phase system, it is called non-minimum phase system. So that's why the name is called non-minimum phase system. So in case of non-minimum phase system, that magnitude and phase, they are not uniquely related, because you can also add some more all-pass terms to that G2 of S, and you can see that the magnitude remains same, but the phase would be different. Phase, it is not that unique relationship, but in this case you would have that unique relationship. That means gain, they are uniquely related in case of minimum phase system, but in case of non-minimum phase systems, they are not uniquely related. So now we'll be just going to the another important concept, that is that systems with transportation lag. Systems with transportation lag. So this particular topic is from actually mathematical modeling of dynamical systems. So here I am just discussing to give you that idea. That means if there is some delay in that loop, or if there is any transportation lag, then what would be the modeling and what is its gain and phase relationship, or what is its that frequency response. So let us understand that what is that system with transportation lag. If we take a simple example, suppose you have a pipe here and you are just mixing a dye. So water is flowing through this pipe and you are mixing, say this is that mixing point, you are mixing dye to that water, and say water is flowing like this. Here water is flowing through this pipe, and you are just monitoring the color at this particular point. So this is that monitoring point. So now it is clear that water is flowing through this pipe. So the time when you are mixing the dye, and if you just look at the concentration YT, so suppose that concentration is YT. So at time t you are mixing it at this particular point and you are monitoring that what would be its concentration. So obviously because of that distance from mixing point to monitoring point, you know that you will get that concentration after some time, and that time is that TD. So this TD is called that delay. Repeating, so this is a pipe and water is flowing through this pipe, and at a particular point you are mixing the dye and you are just monitoring the concentration of that one at some point which has a distance from this mixing point, and because of the distance, the time when you are just mixing the dye T and when you are just monitoring that one, that means getting the what would be the concentration of that, it would be Yt minus Td. That means there would be a delay. So this particular delay is called the transportation lag, and this delay occurs because of the transportation through that pipe. So here if we want to model it, then what would be the output? So output is actually Yt minus Td. So that means here we can write that output Ct equal to Yt minus Td. So this delay is coming because of the transportation lag. So this is called the transportation lag. So now if we take that Laplace transform Cs, so it would be e to the power minus Td of s ys. So now what would be that Cs by ys? That Cs by ys equal to e to the power minus Tds. So this is very important whenever you have some delay in the loop, or if there is any transportation lag, it can be modeled as e to the power minus Tds, that is output by input, that e to the power minus Tds. But you can see that if you expand that e to the power minus Tds, this is actually not finite dimensional, this is infinite dimensional if you see the series of e to the power minus Tds. So it can be approximated, approximated by one transfer function, which is 1 minus Td s by 2 divided by 1 plus Td s by 2. So this is called that first order approximation. So this is called that first order Pade approximation. It has that name, Pade approximation. What is that? So we have seen that whenever there is a transportation lag, we can model it by one exponential term, that is e to the power minus Tds, that is in s domain, and in time domain that is Yt minus Td. And then we have seen that e to the power minus Tds, it is actually one infinite dimensional expression, that is 1 plus minus Tds plus Tds square by factorial 2, like that. This is actually one infinite series. So this particular series can be approximated in first order, that is 1 minus Tds by 2 by 1 plus Tds by 2, and this particular approximation is called that Pade approximation, and a first order Pade approximation. And here you can see that whenever you approximate this e to the power minus Tds, so it is coming in proper form. This is a transfer function in proper form, but you can see that in the numerator there is one 0 on the right half of that s plane. So on the right half of that s plane means here that 0 is at t by Td. So you can see it from here, 2 by Td, that is 1 minus Tds by 2. So s would be equal to 2 by Td. So 2 by Td, there is a 0 on the right half of that s plane. So that means if you approximate one transportation lag via first order Pade approximation, so that transfer function is a non-minimum phase system that we have discussed now. So now we are interested in to see what would be the Bode plot, that means that magnitude and phase plot for the transportation lag. So let us see the transportation lag. So it is model as e to the power tau s. So suppose that is your g of s. So now we know that gj of omega, that would be equal to e to the power minus gj of omega Td. So then that would be cos of that omega Td minus j of sine omega td. So td is the delay. Then what would be the magnitude? So gj of omega, the magnitude would be equal to always 1, because if you see that expression that magnitude is always 1, then what is that angle? So that angle gj of omega, that is equal to that tan inverse that is minus of sine omega td cos of omega td. So that means you will get it as minus of omega td, and here you can see that it is coming in radian. So if you want to get it in degree, so that would be minus 57.3 omega td in degree. So this is that expression that we would have in case of the transportation lag. So let us see, that means if you are asked to draw what would be that gain and phase for transportation lag transfer function, because this is the transfer function that you have seen, that g of s equal to t power minus s td. So what would be that plot? So here you have that log of omega, and it is in dB. So as that magnitude is 1, so in dB scale, so basically that would be 0. So that is 0 all through the frequency. So this is that 0 dB. So that is that magnitude plot. And what would be the phase plot here? You can see here, so this is that log omega scale, and this is in degree. So that is minus 57.3 omega td, and it is in log scale. So basically your plot would be like this. So you can see that whenever your omega is increasing, that means with high frequency, when frequency is increasing, there is always a phase lag. So whenever there is a delay in the loop, or if there is any transportation lag, it contributes some phase lag. So it has lot of effects in stability and performance. So here and if you just plot it degree versus omega, so that would be actually that straight line with that negative slope. So what we have seen here today, so today we have actually started discussing that what would be the asymptotic Bode plot for that second order term, and we have seen that if there is any zeta, there would be some corrections. We have discussed it, and then we have taken one example, and in that particular example we have plotted that magnitude plot, and again I am suggesting you to do that phase plot on your own. Then we have discussed what is non-minimum phase system. So by definition, if a transfer function has a pole or zero on the right half of that S-plane, then it is called non-minimum phase system. But conventionally we take, if the system has 0 on the right half of that S-plane, then it is called that non-minimum phase system. So if there is a non-minimum phase system, so in time response we see that there is a negative kick, and negative, that is called that undershoot. When just switch is on, there would be some undershoot. That is the typical response of a system whenever that system has a 0 on the right half of that S-plane. And here we have seen why it is called non-minimum phase system, because that magnitude and phase are not uniquely related. And we have taken one example. We have seen that G1 and G2, although their magnitudes are same, but that G2S, because of 0 on the right half of that S-plane, it contributes some extra phase. So that's why the phase of that G2, it is not minimum. That's why it is called non-minimum phase system. Then we have discussed what is the transportation lag. That means if there is any lag or delay in the loop, how to model it. So it is modeled as e to the power minus TDS. And we have learned a new thing, that means how to approximate that TDS, because that e to the power minus TDS, it is not a rational transfer function. So to make it as a rational transfer function, we can take first order Paddy approximation. So if we take that approximation, that e to the power minus TDS can be approximated like a proper transfer function, which is a non-minimum phase transfer function because there is a 0 on the right half of that S-plane. And we have seen that if we take the transportation lag transfer function e to the power minus STDS, then what would be its gain and phase? The gain remains same because the gain is constant. So if there is any transportation lag in that system, so gain is not affected because gain is 1, but the phase is affected. We can see that whenever TD is increased, that means if delay is increased at the same frequency, we can see that transportation lag actually contributes more phase lag to that system. So delay is increased, that means we will be having more phase lag. So in the next part of that lecture, we will be just discussing a new topic which is called that Nyquist stability criteria. So that is that last topic from my part. Thank you.